Alright, everyone, welcome back to the afternoon. We'll have Jose Simental Rodriguez telling us about national double affine Hecke algebras.
Thank you, and thank you so much for the organizers for the invitation. So it seems weird to speak about rational DAHA without speaking about DAHA at all. But the point is that you don't need to even define DAHA to speak about the rational DAHA. Type A will be my main example, but I want to restrict type A, partly because even if, as we will see later this week, to define DAHA you need a root system, so you can only define DAHA for while groups. To define rational DAHA, you can do it in much greater generality. So the setting will be as follows. So first of all, I am only going to work over the complex numbers. And I start with the data of a complex reflection group, which is just a finite subgroup of a general linear group. So this is my attempt to write a factor H. So this is a complex reflection group. Meaning that inside of this, W is a finite group, principle. And inside of this, I have a set of reflections. So these are just the elements S and W, such that the codimension of the fixed space of S is equal to 1. And I request for this to generate. Generates W, and for each reflection here, for each S in S, I have an element of the dual of H. So alpha S in H dual will be the element such that this fixed space of S is the kernel of alpha S. We can also characterize alpha S by saying that, if I apply S to alpha S, it's just and S times alpha S, so this is an eigenvector with eigenvalue not equal to 1. And this is defined up to scaling by a non-zero. And so, for example, I can have W to be just a symmetric group acting on C to the n by permitting coordinates. In this case, S is just a set of all transpositions, and alpha S, or alpha ij, is just X to be just a cyclic group. So this is just S, such that S to the L is equal to 1, and this acts on, this H is going to be just a one-dimensional vector space, and here W acts on S by multiplying by an L root of 1. So I pick, for example, let's say eta is e to the 2 pi I over L, and here S acts by multiplying by eta. And here my set of reflections, I shouldn't write over here, right? Okay. And so here my set of reflections S, is just 1 up to S to the L minus 1, so every non-trivial element of my group. And for every S to the I, alpha S to the I, is just a coordinate function on C. And so, to define the rational DAHA, I need one more piece of data, which will be a parameter for my algebra. And this will be a function, C, that goes from the set of reflections S to complex numbers, that is W invariant in the sense that C of W is W inverse, which is not a reflection, is just equal to C of S. So my rational DAHA will depend on this data and this parameter. Operators. that were discovered by Dunkl, and they are important by when solving some quantum integrable systems, well, showing that they are completely integrable. And let me just define them. So now pick, let's say, y in my vector space H. I'm going to define. Sorry? Yeah, thank you. Yeah, yes. So in the case of Sn, so in example 1, I can think just C is just one number. And in example 2, this is an L minus 1 tuple of numbers. Thank you. So in example 2, C is just C1. For this, I guess Ci is just C of S2. Yeah. And so, well, to define the rational DAHA, well, the motivation lies in the theory of Dunkl operators. So for every element of H, I'm going to define an operator that will depend on C, but I will forget that from the notation. The Y, which is going to be the directional derivative with respect of Y, minus some term that depends on this parameter C, minus the sum over all reflections of 2 times C of S divided by 1 minus lambda S. So for example, in this example of W is equal to Sn, I just have C of S because lambda is equal to -1, times the pairing of alpha S with Y divided over alpha S, and I apply the operator 1 minus S. So let's think for a bit, where does this guy live? So it is a differential operator. So it's in some algebra of differential operators, and it has elements of W, so I take some direct product with the group algebra of the group W. And it's not a differential operator on H because it has poles along the kernels of alpha S. So what I can do is I can just remove all those hyperplanes, and so I'm going to define H rect to be just H minus the union of all reflection hyperplanes. Okay? And this is my set H rect, which is actually a principal open set inside of H. So this is a differential operator that lives here, but we can notice that actually when we apply this operator to any function that is defined on the entire H, I still get a function that is defined on the entire H. So note that. Note if F is a polynomial function on H, then applying this Dunkl operator to F, I still get something that is defined on H, essentially because alpha S divides F minus S of F. Okay? So this all cancels when I apply it. And so I can think of these Dunkl operators as being just elements of, well, they're not quite differential operators, so I'm just going to think that they are C-linear endomorphisms of. Okay. And so, well, let me continue with my 2 examples. Let's see what the Dunkl operators are there.
So say when you say divide by alpha S, you apply alpha S to an element of script H and divide by that value?
No, I mean apply 1 minus S, so I'm gonna get something like this, F minus S of F divided by alpha S. And so alpha S always divides this polynomial.
Oh, I see.
Okay. And so in the examples, so.
And what is the sub y?
Oh, this is just the directional derivative with respect of y.
But for this, do you need to somehow have a basis, or?
Not really. You can define it, so it's a derivation, first of all. And so I can just say that, well, this C of H is just a symmetric algebra on H star. I can say that for any element of H star, this is just a pairing. and extend by the Leibniz rule.
H is a vector space, so given any element in the vector space with a canonical directional derivative in that direction,
Yeah.
tangent bundle is trivial.
And extend using the lines. So this is a well-defined operator on this element. And so let's see in these examples what are these Dunkl operators. So in the example 1, well, I have a nice basis, so I just need to say who's this. Let's say dyi. This is just taking the I partial derivative, is what this operator amounts to, minus the sum over all j different from I of C of S divided by xi minus xj times 1 minus ij. And in the example 2,
Did you drop a factor of 2 here?
sorry?
There's a factor of 2 in the numerator?
Oh, there is a factor of 2, but when I have the symmetric group, this lambda is equal to -1, so it cancels.
Oh, I see.
Yeah. And in example number 2, I have well, the y. Here I do have, well, this is just the usual derivative because here I am in a one-dimensional vector space, minus the sum from I is equal to 1 to L minus 1, and here I don't have a way to get rid of this 2. 1 minus equal to the negative I times, well, this alpha is y is 1 divided by x, 1 minus. So these are the Dunkl operators in these two particular examples. And here we can check that actually when I apply these operators to a polynomial, I still get a polynomial.
Excuse me, is it C of S or C of SI?
S to the I, thank you.
And how does S act on the polynomial again? In this case, and this is one variable.
Oh, S, it sends x to eta times x,
Okay, thank you.
and then it's just,
So it's divisible by x again.
yeah, exactly. It's divisible by x again because this kills that constant term. So I'm going to define the rational DAHA. The rational DAHA that depends on this parameter C, HC, is the subalgebra of this huge algebra of C linear endomorphisms of this vector space that is generated by three types of operators. So I have the algebra itself acting on itself by left multiplication. So that's my multiplication. This is a commutative algebra. I have the group W that also acts on this polynomial algebra and the Dunkl operators. So this is what the rational DAHA is. It's just a subalgebra of this endomorphism algebra generated by these three elements, and so by definition it comes with a faithful representation on the space of polynomials. The definition, HC acts faithfully on this polynomial. And so let me give just one example. I'll give a couple more later. Let's see what happens when C is the constant function 0. Then in the definition of Dunkl operator, all of this goes away. And so I have the algebra that is generated by polynomial functions, W, and partial derivatives. And that is just the algebra of differential operators on H. A smash product with W. And I will give a couple more examples in a second. And so note that this algebra comes with 3 distinct subalgebras. So subalgebras of HC. Well, I have the polynomial algebra. It's a subalgebra because of, well, I throw all these operators. The group algebra of W is also a subalgebra of the DAHA, and I can take the algebra generated by all the Dunkl operators. Maybe I should do that on the other board. Number 3. The algebra generated by Dunkl operators and there is a theorem by Dunkl precisely that this algebra is isomorphic to the symmetric algebra on the vector space H, or if you want the algebra of functions on its own. And so this is quite a surprising theorem because this in particular says that the Dunkl operators commute, which is not obvious at all from the definition. And just let me say the hard part is showing that Dunkl operators commute, right? Which in the case C is equal to 0, I guess it's pretty easy, but in general it's not. Alright. Now I can take, for example, the subalgebra generated by those subalgebras 1 and 2. So subalgebra generated by 1 and 2 is just isomorphic to the semi-direct product of CH with the group algebra of W, and the subalgebra generated by 2 and 3 is isomorphic to the subalgebra, sorry, the semi-direct product of the algebra functions on H dual with W. And somehow the interesting part of the DAHA is how do you relate this subalgebra CH with the subalgebra C of H? Okay. And well, by definition, these 3 subalgebras generate the rational DAHA HC, but we have a sort of Poincaré-Verkov width theorem.
Just to make sure, are you saying that isomorphism can be exhibited equivalently by commuting the del I, the D
Yes.
I's with the
Yes.
sign?
Yes. Yes. And this isomorphism is just sending Y to this sub Y. It's like the trivial isomorphism.
Is it easy to see why there's no relation?
Well, it's hard to see that they commute, but after that, essentially, because you have these partial i's, and there are no relations between those. That's no relation. Okay. And so now the PBW theorem for rational DAHA this is due to Etingof and Ginzburg. Says that multiplication gives a vector space isomorphism so I have these three subalgebras CH. I can multiply with elements of the group algebra of W, and I can multiply with elements of the group of the symmetric algebra of H, and this is an isomorphism to HC. In other words, you can find a basis for this algebra by having monomials in H star times an element of the symmetric group times monomials in H. And when we see the DAHA, we will see that for the DAHA we have a similar sort of decomposition, only that here we don't have functions on H, we have functions on the maximal torus. Here we don't have just the group algebra of W, we have the Hecke algebra, and here we have functions on the dual torus. So this is, I mean, there are a lot of parallelisms, and there is a very concrete way in which the rational DAHA and the DAHA are related, but I'm not going to go into that. Okay. And let me mention also, yeah.
It looks a lot like a Heisenberg algebra or Hopf algebra.
Well, the way people think about this, it looks a bit like the PBW theorem for Lie algebras, right? So you have something like this, and so it's more or less analogous to this. I don't know if that answers your question. And we can also present this rational DAHA by generators and relations. So I need just one more piece of notation. So now I take alpha as check, this lives in H, such that S times alpha S check is lambda S to the -1 alpha S check. So this is what gives you the fixed point now in H dual, the fixed point locus in H dual. And well, this is not completely well defined, and I'm going to normalize so that the pairing of alpha S with alpha S check is equal to T. So if you want to think of roots and co-roots, that is right. Okay. And now we can present this algebra HC by generators and relations. The theorem of Etingof and Ginzburg. Says that this algebra HC is isomorphic to the following algebra. So you take the vector space H plus H dual, take the tensor algebra of this vector space, do semi-direct product. Well, I have the more or less boring relations that say that elements of H commute and elements of H star also commute. And the interesting relation is how an element of Y passes through an element, how an element of H passes through an element of H star, and this is the pairing Y, X minus the sum over all reflections of C of S alpha S, Y, alpha is check, comma x times s. And here, all the y's belong to h and all the x's belong to x star. So this is a presentation of the rational DAHA by generators and relations, which may not look so nice, but let's try to unravel this in the two examples, which are the symmetric group and a cyclic group acting on a one-dimensional vector space.
So is it the multiplication? Alpha s comma y times alpha s check comma x, right?
Yes, times
Okay.
alpha s check times s.
Mhm.
Yes. Okay. So I have my two favorite examples for the symmetric group. So let's say when W is equal to Sn, so I have that this Hc, remember here C is a single complex number. And well, I'm gonna have a free algebra on 2n variables. Then I do semi-direct product with the group algebra of the symmetric group, where this permutes both x's and y's. And now, well, I have that xi, xj is equal to 0, which is the commutator of yi with yj. If I try to commute, let's say yi with xi, I don't get this term. This is equal to 0. And here, I'm going to get the sum over all j not equal to I of c times ij. Sorry, what am I saying? This is yj xi. So this is just c times ij. That is the only term that will survive here. And if I try to commute yi with xi, now I do have 1 minus c times the sum over all j's equal. That is different from I of ij. So this is a concrete presentation of this Cherednik algebra by generators and relations in the case of the symmetry. Okay. So here I have essentially that this alpha s is xi minus xj, so only, let's say, when I have xi will survive, and here alpha s check is yi minus yj, and so on. Only this term. In the other case, second case, when I have W is a cyclic group, then my Cherednik algebra, remember that here C is an L minus 1 tuple of complex numbers. And so a presentation of this algebra by generators and relations is going to be, well, I have 3 generators, x, y, and s. The relations here are that s to the L is equal to 1. Then I have the semi-direct product relations, s, x, s inverse is eta times x, s, y, s inverse is eta inverse times y. And now when I try to commute y and x, I'm going to get 1 minus the sum I equals 112 minus 1 to ci times s to the I. And this too comes from my normalization checks. Here I have it. Okay. And so this is a presentation of this Cherednik algebra by generators and relations. Are there any questions? Okay. If not, then let me move on to the representation theory of this algebra. I don't want to raise. Oh no, I still have a couple more things to say, sorry. So a couple remarks. First remark is that this algebra HC is filtered. It's a filtered algebra. where I put, let's say, W in degree 0, sorry, and both H and H star in degree 1. And when I take this, the associated graded of this algebra is canonically isomorphic to just the symmetric algebra in H plus H star, semi-direct product with the group algebra of W. So this is, I mean, when C is equal to 0, this is pretty easy, and it more or less follows from this PBW theorem. Well, not more or less, it is equivalent to this PBW theorem that we have this associated grades. But the algebra is not only graded, sorry, it's not only filtered, it's also graded, and this will be very helpful. So this algebra HC is graded. Well, I can observe the relations, and if I put W in degree 0, H star in degree 1, and now H in degree negative 1, I get a grading. These relations become homogeneous. And what is surprising is that this grading is inner. Meaning that I can find some element in the algebra that I'm going to call H as some sort of Euler element, defined as follows. So I pick a basis of H, dimension H, xi, yi plus yi xi over 2. So these x's are a basis and y's are a dual basis, and it's not hard to see that this does not depend on the chosen basis. And well, if you like, we can use the relations to write this element as follows. Minus the dimension of H over 2. And now, I need to be careful here with my notes. Minus the sum over all reflections of 2CS divided by 1 minus lambda S times S. So it's a nice exercise to use the relations to check that these two expressions are actually. And it's another nice exercise to check that this element does give a grading here. In other words, that we have that H commutes with the group W. If I try to commute H with an element of H star, I just get X again. And if I try to commute with an element of H, I get negative Y. So I have an inner grading on this side. And now I'll move on to representation theory. And most of the representation theory of this algebra has been done by more or less mimicking the construction of highest weight modules for this enveloping algebra. So I'm going to define a category which is very analogous to the category O for these algebras. If you know it, great. If you don't worry. So I'm going to define the category O, also OC if I want to specify the parameter, to be the category of finitely generated modules over HC of finitely generated HC modules with a locally nilpotent nilpotent action of the elements of H, of the Dunkl operators, if you want, with a locally nilpotent action of H. And so this is more or less analogous to category O, where you have category of models which are T semi-simple and with a locally nilpotent action of n minus. Here we don't need to ask for the T semi-simplicity because our total subalgebra is already semi-simple. Okay. So an example of a module in this category. Well, remember that this rational DAHA comes equipped with a module, which is just this polynomial algebra. So example, well, this polynomial representation belongs to this category. Because, well, we have to check that Dunkl operators act locally nilpotently, but by their definition, Dunkl operators reduce the degree of a polynomial by 1. And so it acts locally. It's not nilpotent, but locally. Any questions? Here? No, I do mean H. So, no, Dunkl operators are H. So I have this algebra, which is just a symmetric algebra on H star. And the algebra generated by Dunkl operators is technically, I guess, functions from H2O, which is a symmetric algebra on H. So these are the Dunkl operators. So I have one Dunkl operator for an element of H, not of H star. So again, Dunkl operators reduce the degree of a polynomial by at least 1, and so it acts locally nilpotently. Here, it is, well, it is clearly finitely generated, so it is a module in this category. And the cheapest way to construct modules in this category O is by mimicking, again, the construction of standard modules for the algebra. Well, I'm going to recall how you do that. So standard modules or Verma modules. We have to start with a simple representation of my Cartan subalgebra. In this case, it's just a simple representation of W. So let's start with lambda, an irreducible representation of W. Then we have to inflate to our Borel subalgebra by letting the Levy act by 0. So what we do here is extend to a representation of CH star semi-direct product with W by letting H act by 0, and then I have to induce, and that's how we construct Verma modules. Verma module delta of lambda, delta C of lambda, if I want to specify the parameter, is by definition just induced module here. And let me just remind you that this induction is just a tensor product. So this is HC tensor product over this, sorry, it's H. Let me keep to one convention. This representation lambda. And it looks complicated, but actually as a CH module, this is quite simple. By the PBW theorem, I have that this module is actually equal to just this free module as a C of H module. if I ignore the action of Dunkl operators and of W, this standard module is just a free module over. And so, for example, that polynomial representation I have over there. So, for example,
Now, when you mean lambda, it's this thing there or not?
sorry.
When you mean what is that? Is lambda C of H star Simental W or not?
Lambda is a representation of this value. So lambda is a representation of W.
I'm taking it back.
That then I inflate to a representation of this algebra by letting H act by 0.
So lambda is just a finite dimensional vector space on which W acts.
Yes, yes, exactly, yes, yes.
Thank you.
And then I induce to a beta.
So it would be trivial in this example.
Yes. So if I do this Verma for the trivial that we have been noting like this, I think, then I just get this polynomial representation. Okay. This equality is not just as a CH module, it's actually as a graded CH module where I have to specify the grading as follows. So inside of this vector space, I have just, well, I can take the polynomial 1 and this is in particular a W subrepresentation since this element H down here commutes with W. It has to act by scalar here. That I'm going to denote C sub lambda, if that is not too confusing, on this space. But then it follows that I can actually diagonalize the action of H on this module. So then the H action on delta lambda is diagonalizable with eigenvalues of the form C lambda plus some positive integer, some non-negative integer, sorry. And I can actually tell you what is the eigenspace with eigenvalue C lambda plus k. This is just going to be homogeneous polynomials of degree k. So this is just a space of homogeneous polynomials of degree k. Essentially because multiplying by an x raises the degree by 1. Okay. So this is homogeneous polynomials of degree k. So I have a bunch of graded free modules. Well, the grading is not by integers because this C lambda can be just arbitrary complex numbers, but it's not too bad. It's just shifted by some. And since this grading is inner, note that any submodule of delta lambda is graded. And then it follows that this delta lambda has a unique maximal submodule. Because, well, unless if a submodule touches this C lambda part, then it's everything. And so that's the reason, more or less. And so then delta lambda has a unique irreducible quotient that I'm going to call L.
Excuse me, can you say again what you mean by any submodule is graded? I mean, why can I not stupidly, just take the sum of two vectors of different grading and take the one-dimensional subspace generated by the sum of two vectors?
But then I have to generate an HC module with that, so I have to multiply by every element of HC. And what I get at the end, it has to be graded. Because it has to still be graded by eigenvalues of H.
Okay.
So on. So any submodule is graded. And
why does this imply that it's a unique irreducible quotient?
Because if you have a proper submodule, then it cannot touch the C lambda part, the part in degree C lambda. If it doesn't, you just generate everything. Okay? And so the sum of all the proper submodules won't touch that C lambda part, so it has to be proper.
And why is that part irreducible?
Well, because I am adding over all proper submodules, that has to be a maximal submodule.
It could be 0.
Yeah. It could be simple. Yeah. I mean, this delta lambda could be simple to start with. Yeah, it could be simple. Thank you.
Okay, can I make sure I understand? So
Yeah.
in the case that the original complex function lowercase c is 0, this k is the weight grading induced for the usual Weil algebra.
Yes.
And so how does c lambda play with the lowercase c? Like, I could imagine, given any action of w on lowercase lambda, I could write down this decomposition.
Mm-hmm.
But is there something special about c lambda that's not just about capital W and lowercase lambda, that's c lowercase c?
Sorry, can you repeat this?
Yeah. So when lowercase c is 0, I could have written the exact same thing.
Yes.
Where c lambda there depends only on my choice of capital W and lowercase lambda.
Yes.
When lowercase c is non-zero, does c lambda get changed from the naive thing I just said?
Yes, it does. And I'm going to compute this C lambda in the case of the symmetric group in a couple of minutes, and then we'll see how this is getting. So I have a unique simple quotient, and these simple quotients just are all the irreducibles in this category. So this lambda is a complete list of irreducibles in these categories. So it has the same number of irreducibles as the group W, but here we can have, initially we do have non-trivial extensions. So it is like a meaningful deformation of the category of representations of W. Okay. So let me compute this C lambda.
So H acts by C lambda on this L of lambda, is that right?
Not just by C lambda. So the eigenvalues of H on L lambda are definitely contained in this set C lambda plus K. But I mean, for example, it could be that delta lambda was already irreducible to begin with, and then you have all these eigenvalues. So that's all we know. H doesn't act just by a scalar, but the action is still diagonalizable, and the eigenvalues are at least contained here.
Generic parameters are the semi-simple.
Sorry?
For generic parameters, is it semi-simple?
For generic parameters, it is semi-simple. Yes. I'll try to mention why. Okay, so let's take again W is equal to Sn, and here, well, irreducible representations of Sn correspond to partitions of n. And so let's try to compute what is this C lambda for a partition lambda. Okay, so I have to see what is the eigenvalue of H on this representation. Let's say S lambda. So I have to see how H acts here. But remember that, well, by definition, yi's are going to kill 1 tensor S lambda. So I just need to see how the part that I erased, sorry. So this is some 2C S 1 minus lambda S acts here. And so I have to see how negative C times the sum of all reflections acts on this one. And here I will rely on results on the representation theory of the symmetric group. So so there are these elements inside the group algebra of the symmetric group called the uses-morphic elements. And this element here is just negative C times the sum of all the uses-morphic elements. So this uses-morphic element this is morphic I is just the sum over all j less than I of the I. So uses-morphic 1 is 0, uses-morphic 2 is 1, 3, uses-morphic 3 is 1, 3 plus 2, 3, and so on. Okay? And, well, the action of these elements on this representation as lambda is diagonalizable. And, well, remember that S lambda has a basis consisting of a standard tableau for lambda, and if I multiply this ith uses-morphic element by some standard tableau that I'm going to denote by frac T, this is simply going to be the content of the box that is labeled by I will define the content in a second, times this standard tableau, where the content of a box is just column minus row or row column minus row.
Yeah, so the 0 on the main diagonal,
Yes.
and 1 on the super diagonal.
I'll make an example in a second. So if I apply this sum of uses-morphic elements to a single standard tableau, I'm just going to get the sum of all the contents of all the boxes. Okay? So the way this H acts so this C lambda is going to be, well, n over 2, negative n over 2, minus C times the sum over all boxes in the Young diagram of lambda of the content of lambda. Okay. So this is a very easy thing to compute once you have the actual tableau. And just, it is true that this category is most of the time semi-simple. So let me observe. Note, if, let's say I have two irreducible representations of my group W, mu and lambda, if, let's say the representation L mu appears as a simple constituent, as well, appears in a Jordan-Hilbert series, for delta of lambda, then again we can use the H degree. Then it has to be that C mu is equal to C lambda plus K for some K, which is greater than or equal to 0, and greater than 0 if mu and lambda are not the same representation. And so, yes, it follows that for generic values of the parameter C, well, I can arrange so that this thing is never true. And so for generic values of the parameter C, the category will be semi-simple. But not for all values. And also note that, okay, I'll come back in a second. So for generic values, of C, the category of C is symmetric. And just note that this condition is necessary, but it's not sufficient at all. So it might be the case that I have this equality for some lambda mu, but the category is still semi-simple. And there is a nice way of testing when this category is semi-simple that has to do with Hecke algebras. And I cannot do it justice in 5 minutes, but I'll try to at least tell you that an idea. So I define my algebra HC as a subalgebra of endomorphisms of this vector space. But I can also think of this algebra as being contained in differential operators on the regular locus, semi-direct product with W. Because this is where Dunkl operators actually live. Okay? Now, I can pick any polynomial whose zero locus is precisely the union of the hyperplanes, and I can localize by that polynomial. And that polynomial is precisely the product of all the alpha s. And the formula for the Dunkl operators shows, well, this inclusion shows that I can localize by delta even if this algebra is non-commutative. And the formula for the Dunkl operators show that when I localize by delta, I get this entirely. So HC localized by delta is precisely this So what I can do is I can take a module in category O. I can localize by delta. And I get a module over this algebra. And more or less by the definition of the category O and the PBW theorem, it follows that this is actually finitely generated over functions on H ray. And so this is actually a vector bundle on H-reg, well, a doubly equivalent vector bundle with a flat connection. Now, since the action of W here is free, I can move to the quotient without losing any information, and then I can take monogram. So I can now move to the quotient. So and then I can take monodromy, and I get a representation of this group. But this is precisely the braid group, at least in the case of the symmetric group. And let me just say for W is equal to Sn, applying this procedure, to a module in category O, well, it will yield a representation of the braid group, but not only that, will yield a representation of the Hecke algebra. Well, remember that this is going to be the algebra generated by T1 up to Tn minus 1 by divided by braid relations And here I take a different normalization from the one that Monica took yesterday. Here I heal the polynomial ti minus 1 times ti plus e to the 2 pi square root of negative 1 6. So the action of this braid group will factor through this algebra. And this is one of the main tools used in the representation theory of this Cherednik algebra. In particular, the category O will be semi-simple precisely when this algebra is semi-simple, which is when this number is a root of unity. Sorry? Yeah, I think it's not a root of unity. Yes. And so, sorry for being too fast here, but I guess that's it.
Can you say once more, what is this representation on? Is it on a finite dimension?
Which one?
What is this break representation on? On what space?
Oh, it's gonna be the fiber of this vector bundle. Just pick a fiber of this vector bundle on each rect, which is finite dimensional, yes. So once you localize, you get a vector bundle on each rect with a flat connection. Take
What's
a
the
fiber.
dimension of that bundle?
Sorry?
What is the dimension of that bundle?
In general, it's not so easy, but if you start with a Verma module, the dimension will be the dimension of the reducible representation of the reducer. So if you start with delta lambda, then delta lambda delta inverse is a vector bundle of rank, the dimension of lambda. But in general, it's hard to determine that. Like for a simple, it's hard to determine.
Can I make sure I understand the story? So you showed us how we begin with a representation of affine DAHA, and once we localize, we get a module over this one, which you're also calling a Hecke algebra. But I guess that's one of the and then you said something like this is how we show that the representations of the Hecke algebra is semi-simple. But you only showed us that for this affine DAHA, right? For generic values of C.
There is some work to do. For example, one can show that this functor is essentially surjective, and that will show that whenever the category is semi-simple, then the Hecke algebra is also semi-simple.
I see. And I don't know enough yet to know why representations of the spray group have to do with modules over this Hecke algebra.
Well, this Hecke algebra was defined yesterday to be a quotient of the group algebra of the braid group.
Yeah.
So what I'm saying is that every representation I get of this braid group, if I start with category O, will satisfy these relations. And so it's actually a module over this Hecke. Yeah.
So you have this function from RCA for DAHA to your Hecke algebra over separation of the braid group. And you just said it was subjective. What can you say about like playing the picture in reverse? Like, how are you able to relate representations of your Hecke algebra back to DAHA?
That is actually pretty non-trivial. So essentially, you have to check first that it is surjective for rank 1 groups, which is not hard. And then you have to apply a gluing procedure. So you have to go reflection hyperplane through hyperplane to glue something to get a modular category. And this is non-trivial, but for example, this is how you show this Brouwer-Mallet-Rouquet conjecture that the dimension of the Hecke algebra is equal to the cardinality of W in the most general case. But yeah, it is not easy.
Are there any other questions?
Maybe one more. So, what is what does the word rational mean here?
So we will see that the full DAHA at some point, I guess, on or before Friday. And so the full DAHA also has a triangular
So it's
decomposition.
not this delta minus 1 over there.
So it doesn't have to do with this delta minus 1. No, it's a double step degeneration of this full DAHA. And so it's, I guess, instead of having functions on a torus, you have functions on just a flat space, and that's why it's called rational.
And this is the rational threatening to T equals 0.
Sorry?
Just to clarify, this is the rational DAHA is isomorphic to your rational threatening algebra.
Yeah, it's the same. Yeah. And here, I only went for the experts. I only took T equals 1. There is a different version of T equals 0 that has a very different story behind it.
Alright, well, let's thank us again. And now we have a coffee break until 3:30.